Hi everyone, this is Hal Tasaki. Today I'd like to talk about our somewhat older work on non-equilibrium statistical mechanics. So it's a joint work with Terihisa Komatsu, Naoko Nakagawa, and Shinichi Sasa. So these are the two main papers. And when we wrote these papers, we sort of believed that this work would lead to a new direction in non-equilibrium physics. But now I have a feeling that we were stuck at some stage, so no essentially new results. Nevertheless, I'm giving this webinar in 2020 because I still believe that there is something interesting in this work. And so I hope you will find it interesting, and I sincerely hope that you will come up with a new idea that will lead to a new breakthrough. Okay, so the talk has another title. I'm going to talk about two twists in steady state thermodynamics. You will see what these two twists are. So motivation. Let me start from equilibrium thermodynamics, about which we all know about. So we consider a system uh, which has a controllable parameter nu, or the set of parameters nu, like the volume, external field, and something like that. And now assume that the system is attached to heat bath, which must be huge, with some given inverse temperature beta. So you start from the equilibrium state with inverse temperature beta and the parameter nu. Okay, and at some stage, we make a sudden change of parameters, temperature and parameters, to beta prime and nu prime. And then the system is no longer in equilibrium. But if you wait for a sufficiently long time, then of course it relaxes to new equilibrium state with this new beta prime and nu prime. And now by delta Q, we denote the energy transferred to the bath from the system during this relaxation process. Of course, that's heat. Then you know that the Clausius relation is valid. The difference in the entropies of the final and initial state is basically equal to delta Q divided by T. Okay, so this, as you know, was the starting point of the whole theory of thermodynamics. Now, I want to look at non-equilibrium situation. So on the same setting, let's suppose that these temperatures of the bath are different. And now if you fix beta 1, beta 2, and the parameter nu, and then it is expected that after the long time, the system approaches a unique stationary state, which we call non-equilibrium steady state, NESS. Okay, and here's the comparison between equilibrium and NESS. In both cases, we have no macroscopic changes at all, but in equilibrium state, we have no macroscopic flows. But in NESS, we do have non-vanishing macroscopic flow of energy or matter, like here. Here, heat is flowing. Now, so suppose that we have a NESS with this temperature beta 1, beta 2 nu. And as in equilibrium case, we make a sudden change of these temperatures and parameters at some stage. And of course, the system is no longer in NESS, but if you wait for a sufficiently long time, you expect that you will reach another NESS, new NESS. And now we want to ask, is there anything like the Clausius relation associated with this non-equilibrium relaxation process? And the main result of this talk is a derivation based on general microscopic models. So a typical system we are looking at is a system of n classical particles confined in a box. And by Ri, we denote the position, Pi, the momentum of the ith particle. And by lowercase x, we denote the collection of all the positions and momentum. Okay, so this is a huge, big quantity. And we assume that the system is attached to two heat baths. So the time evolution of the system is described by two parts. One is a usual Newton equation with potential V. And we assume for simplicity that this external force potential contains this controllable parameter, like external field, volume, or whatever. And here's two-body interaction. Okay, but this can be almost anything. And this is deterministic part. And the stochastic part, here we have stochastic part, which is basically Markovian time evolution, which describes the effect of the walls having temperatures T1 or T2. So the most standard thing is to use Langevin dynamics only near the walls. And or you can use something called thermal wall that I'm going to explain in the next slide, or anything else. But the only assumption we need is that this Markovian time evolution satisfies a local detail balance condition. This is a very standard terminology in non-equilibrium statistical mechanics, so you can find it in any reviews or many papers. Okay, so and all of this satisfy local detail balance condition. Just one word about thermal wall. It's an especially designed wall which describes a body with temperature T. So whatever the initial velocity is, the particle is, it forgets the velocity, and it will come out from the wall with a new velocity V out, which obeys this probability distribution. Then this describes the effect of wall with temperature T. This is standard. And also here, note that you can compute this energy difference. And this can be interpreted as the microscopic heat transfer from the system to the bath. So if you sum this Q up, you will get the total heat. Okay, or you can compute heat current and so on. That's important. General setup. Okay, so these are parameterization. So the control parameter, we denote by alpha the collection of two inverse temperatures, beta 1, beta 2, and this model parameters like the volume or the external field. It's like this. And X, the state of the system is this, and this is important. By X star, I denote the time reversal of X. So R are the same, but you reverse all the momenta. Okay, and we assume that the energy of the system is invariant under time reversal. And here comes time evolution. T is the time variable, which runs between 0 and tau. Tau is a big quantity, which is fixed. And this is a basic important assumption. I assume that this alpha parameter is a function of temperature. That means beta 1, beta 2, and nu are functions of function of time, T. And these functions are fixed before the experiment. So that is usually called protocol. So before running your experiment, you decide how you change the temperature, so how you change the volume and so on, and you probably program these changes. That's called protocol. And then experimental setup just obeys this. And by alpha hat, I denote a whole function. Okay, and so this is something you decide and you determine. On the other hand, X hat is something system determines by solving the equation of motion, and also it's stochastic. Okay, but by X hat, I denote the whole path. And then since the dynamics is Markovian, you get something called the path probability density for each realization of path, which of course depends on alpha hat. Okay, and so this roughly speaking, this is a probability that you get a specific path X hat, and it's normalized in this way. So if you fix the initial condition and sum up over all the paths, then you get 1. Okay, so again, this is a standard object, and I say that this T path probability density satisfies a very interesting symmetry called detailed fluctuation theorem. And here I have new notation. By alpha hat Dagar, I denote the inverse protocol. Inverse protocol, simply the time goes in the opposite direction here. And X hat Dagar is the inverse path, the reversed path. And again, time goes backward, and also I take this time reversal. Okay, and then I say that this equality is valid, and for this probability density for the forward path and probability density for the backward path. But here you have some new quantity that I have to explain. This theta here is called the total entropy production in the bath. In the simpler case, when the temperatures of the bath are kept constant, it's simply the total entropy production. So Q from system to 1 is the total amount of heat that the bath 1 absorbed during this process. So this is the entropy production, and this is for the second thing. And in general, when the temperature of the bath is time dependent, and then you consider this quantity, which is entropy production rate in the ice bath, and you simply integrate. Okay. By this way, you get the total entropy production in the bath. And this is the time of quantity we are looking at. First of all, we assume that when the parameters are kept constant, the system eventually converges to a unique non-equilibrium steady state NESS. And I denote by rho alpha of x. Alpha is the parameter, x is the state of the system, probability distribution of NESS with parameter alpha. Okay. Now, suppose that we are interested in any function f of the path. Okay, and then we consider this time average, this average, which depends basically only on this protocol alpha hat. What is this? Well, it's here. You start from the NESS for the initial parameters alpha 0. Okay, so you are first you are in NESS with parameter alpha 0, and then you start your protocol and you start changing your alpha, and the system changes. The state of the system changes according to this, and then you simply average. Okay, so yeah, you start from a NESS with alpha 0 and just do your protocol and consider the average of any function f of the path. Okay, so that's a basic setting. And now I'm ready to talk about the Clausius relation, the original Clausius relation, and the extended Clausius relation of ours. So this is the equilibrium case that everybody already know. So this is a simple step protocol. You start from beta beta nu. The temperatures are the same, so this is equilibrium condition. And at some stage, you change it to beta prime nu prime. Okay, and delta denotes the amount of change. And then in this case, for large enough tau, we can prove, or many people can prove, this was proved many, many times, that the difference in entropy is equal to the minus of the total entropy production in the bath. And here the entropy is just thermodynamic entropy. It's a Shannon entropy of rho. In this case, rho is just a canonical distribution. So it's a very standard thing. And in this case, this has a simple interpretation. So this is a total entropy production. So it means that this is a difference of the final entropy and the initial entropy of the bath. So this equality can be rewritten in this way. So this simply tells you that this is the initial entropy of the system plus bath, and this is the final entropy of the system plus bath. Okay, with some minor error coming from this step protocol. So this simply says that the total entropy is constant. But I will say that this is no longer true in NESS because we have a constant entropy production. What is this? Well, so consider a steady, non-equilibrium steady state NESS. So we have this steady situation with steady heat current, which is proportional to the temperature difference. And now this is the entropy production rate. Beta 2 J stationary, this is the entropy production in this path, and the heat is going in this direction. So this is the entropy production in the first path. And now, since J is proportional to beta 2 minus beta 1, this entropy production is proportional to the square of the temperature difference. That means it's strictly positive. This means that the entropy production rate is 0 only when the temperatures of the two baths are the same. This is the equilibrium case, and it's strictly positive whenever the temperatures of the two baths are different. So NESS is accompanied by a constant non-vanishing entropy production in the bath. That's very important. Now I ask if there is like something like Clausius relation for NESS. So let's consider this step protocol that we considered before. Uh, First, we have our parameter is beta 1, beta 2 nu. And at some stage, at time tau over 2, we change the parameter suddenly to beta 1 prime, beta 2 prime, nu prime. Okay. And now we ask, is it possible that we have this kind of relation? So we don't know what these are. What this entropy is. This is a non-equilibrium entropy, but can we ask if there's if is it possible to that this kind of relation is valid? But the answer is definite no, because whatever this non-equilibrium entropy is, this is simply the difference of the two entropies in two nests. So this difference is of course independent of tau. But here on the right hand side, you have entropy production, total entropy production. So since we always have entropy production in nests, this guy is proportional to tau and diverging in tau. So this is independent of tau and this is diverging in tau. So we never have this kind of relation, divergence. So this is a schematic picture. This is a entropy production rate, and this is a case of operation in equilibrium. So in equilibrium case, we start from equilibrium. So the entropy production rate is 0. And then here you make this operation. So the system is no longer in equilibrium. So you have non-zero entropy production, but again, relaxation process. And again, the entropy production becomes 0. So in this case, if you integrate this quantity, you get something finite. This is the total entropy production. Now, this is a case of NESS. You start with a NESS, so nothing, no operation, everything is steady, but you always have non-zero entropy production. Here you make operation, some relaxation process. Here system has relaxed to a new NESS. No, nothing changes, again steady, but still you have to pay this amount of entropy production rate. Okay, so you always have to pay some amount of non-entropy production rate. So if you integrate this, of course, you get some diverging quantity. What shall we do? Well, so this is a diverging quantity. So what we learned is that whenever you have a diverging quantity, you subtract something, renormalize to get finite quantity. In this case, it's very natural to subtract the area of this part and consider only this thing. And this, the remaining finite quantity is called excess entropy production. What did we do? Well, as I said, if your parameter is alpha prime, you know that you must at least pay this amount of entropy production to maintain NESS, steady situation. Here you don't have anything steady, but here you have steady state. And we know that in order to maintain steady state with this parameter alpha prime, then you have to pay this amount. So we know that we have to pay this amount. So you simply subtract this. And here, this is the amount that you have to pay, so you subtract this. So we are left with this finite quantity. In general, this subtraction can be written in this way. So this is a bare entropy production, which is divergent. Here, this is the entropy production that we expect. So sigma ST alpha is the entropy production rate in NESS, in a steady situation with parameter alpha. So this is the entropy production rate that we expect from the parameter alpha t. So we simply integrate this and subtract. This is this pink part is this. Okay, and then you are left with hopefully finite quantity. Okay, so that's our renormalization. Okay, this is a divergent quantity. You subtract another divergent quantity, which you can determine from your parameter, and then you are left with this excess quantity, which reflects the relaxation process of the system. And then, yes, we do have extended Clausius relation. So this is our protocol. We change parameters suddenly, and then we say that there is certain function, non-equilibrium entropy, and their difference is basically equal to the minus of this excess entropy production, renormalized finite quantity. There is some error term. This is familiar error term coming from the STEP protocol, but this is new one. And here epsilon is the degree of non-equilibrium, basically the difference in temperatures. Okay, so here, so this is vanishing in equilibrium situation, but we do have this. Okay, and so what is this non-equilibrium entropy? That's interesting. It's related to the probability density by this relation. And what is this SM? SM is something very similar to the Shannon entropy, but with extra symmetrization. Okay, in Shannon entropy, we had simply rho x log rho x. But here we have square root rho x star. This is simply the time reversal, time reversal of this probability density. And recall, in equilibrium, the equilibrium probability density, that is the canonical distribution, is invariant under time reversal. So in that case, rho x star is rho x. So this square root thing doesn't matter. But in non-equilibrium case, this does matter. And so without this square root thing, with only Shannon entropy, we never get extended Clausius relation. And with this twist, okay, so this is the first twist. Thank you for waiting. This is the first twist. Instead of using Shannon, we had to make this small but very suggestive twist to make this extended Clausius relation possible. Okay. Now it's just automatic, but as usual, we can think about slow and gentle protocol alpha, which changes slowly and smoothly. And it connects this value and this value. And in this case, our extended Clausius relation becomes like this. And unfortunately, here we have this term. So if epsilon is 0, this is not here. So it's just usual Clausius relation. But now we are in non-equilibrium situation, so we have this error term. Okay, so here anyway, we have a natural extension of the traditional Clausius relation in which divergent bare entropy production is replaced by its renormalized counterpart, the excess entropy production. And as I said, this is meaningful only when epsilon is small. So we have to be close to equilibrium. Now with this, we can think about operationally determining the entropies of NESS. So first of all, let's think about an operation which brings equilibrium state into a non-equilibrium state like this. So to realize this, you simply fix beta 1 and nu and only change the temperature of this right heat bath from beta 1 to beta 2. And here I can use and slowly, gently, okay? You change this temperature slowly, gently to beta 2. And then you start from equilibrium and you end up in NESS. And in this case, this is our extended Clausius relation. But in this case, delta, the change in parameter is basically epsilon. So this error term becomes order epsilon cubed. This means we can determine the non-equilibrium entropy to order with the precision epsilon squared only by measuring the heat current. That means this thing here is in principle this thing here can be in principle determined by measuring heat, right? You just draw this and you just subtract and so integrate and so on. So this tells you that by doing this experiment and measuring heat, you can determine this difference. And of course, this is equilibrium entropy, so you know this, so you can determine this thing. Okay, next, let's think about comparing entropies of two NESS. Okay, so now I fix beta 1 and beta 2. Okay, and they are different. And now I think about changing this nu, like the volume or external field. So this is a okay. Here I have fixed the temperature of the left bath to beta 1, and here only I did depict temperature of the right bath. But here the temperature of the right bath are the same, and I only change the parameters. And I want to compare the entropy here and here. Okay. And now, if we use our extended Clausius relation in this situation, so I fix two temperatures and I gently change nu from nu to nu. from new initial value to new prime. Slowly change the volume or slowly change your external field. And then we have this relation. But in this case, delta is of order 1. So this Euler term becomes order epsilon squared. So this means that we can determine the difference, but the precision is simply order epsilon. That's sad. But we can think about doing something else. So we want to get to compare this point and this point. And we first thought about going here and to here directly. But instead, you can take an indirect path. You start from here and go here first, and from here to here, and from here to here. So this is here. And then you can use, first of all, our extended Clausius relation here. And here, this is the equilibrium. This is just a usual equilibrium isothermal operation. So you can use usual Clausius relation, and here use our extended Clausius relation between equilibrium, between equilibrium and NESS. And in this case, what we get is this. So here again, these are the quantities you can determine by measuring the heat current. Oh, everything, yes. These are the quantities that you can determine by measuring heat currents. And we can determine the difference in entropy with higher precision, order epsilon squared. So to summarize, possible errors in each process is, if you go directly, that error is possibly order epsilon squared. But if you go in this way, error is smaller here, and error is 0 here. Okay. So this is a bit weird. So you of course ask, can't we do better here? And yes, we can. So we are coming to almost to the final part. So I'm going to talk about new nonlinear non-equilibrium relation. Actually, we can, yes, we can prove a better improved extended Clausius relation type equality for this particle. You fix temperatures beta1, beta2, and you change nu, like the volume or external field, slowly, gently from nu to nu prime. And then this is valid. The same non-equilibrium entropy, the same excess entropy production, and something new. Here, W denotes the work done to the system. The work done to the system during the whole protocol, okay, during the whole operation. And theta is, of course, the total entropy production in the bath. And here, this W semicolon theta denotes the truncated correlation. Okay, but anyway, so this contains correlation function, but this has a higher precision. So this relation takes into account nonlinear non-equilibrium contribution and has a desired higher precision. That's nice, but it contains a correlation between heat and work. Okay, so anyway, it's a relation between macroscopic quantities. We only have, so these are macroscopic entropies. These are all macroscopic quantities. I mean, they can be determined by measuring heat and work. Okay, but it only contains a macroscopic quantity, but can we call such a relation containing correlation a thermodynamic relation? That's something we don't know. We still have to think about. And now, so this is a summary for the operational determination of entropy. So suppose that we want to determine the difference of this two non-equilibrium entropies with a precision order epsilon squared, then you can do it either going directly from here to here, or you can go from here to here indirectly like this. But isn't this a twist? Because in order to get this same precision, you have to either use first order relation or the second order relation, depending on the path you take. This is a very weird twist, which is again suggestive, but we still don't understand what does this mean. So here comes my summary. So first of all, I have to note that our results are mathematically rigorous for Markov jump processes. But for other things like Langevin dynamics, it is our results are not entirely rigorous. It's almost nice from theoretical physics point of view, but from mathematical point of view, they are still not rigorous. But anyway, we found a natural extension of Clausius relation for operations between NESS, which enables us to operationally determine non-equilibrium entropy to the second order in the degree of non-equilibrium, epsilon. And the non-equilibrium entropy has an expression in terms of symmetrized Shannon entropy, a twist. This is very suggestive, but we still don't know what this means. Okay, so the basic question that we have to ask, and which we are asking always to ourselves, is that is there meaningful thermodynamics for NESS, which yields non-trivial experimental predictions? Ours still do not make any non-trivial predictions. That's the big problem. And of course, there are many different, probably promising attempts by many others, but this will be a different story. So I think I have said everything that I wanted to say. So thank you very much for watching, and goodbye.